And we're going to look at some special kinds of exponential functions, aka equations, if that's what you'd like to call them. We're going to look specifically at two different types today. One's going to be a growth function, and the other is going to be what we call a decay function. The first one, take a look at, we're going to start with the growth piece. Because some of you are probably wondering, okay, Miss Guy, so this graphing stuff we do, the work with exponents and things, when would that come about? And that's what we're going to take a look at today. So we have the first one is our growth function. I have the basic form there for you. The y equals a times the quantity 1 plus r to the t. And then on your sheet is already listed what each part of that function represents. So the y is going to be our final amount. The a is our initial amount, or if you guys want to, you can relabel that as your starting amount if you want. If you don't like the word initial, if starting or beginning makes more sense to you. If you're good with initial, that's fine. The r piece, the r is your rate of growth, and it is in decimal form. You're going to have to change a percent to a decimal. So your rate of growth is going to be given to you as a percent. You're going to have to change it to a decimal. We'll do that a couple times today. If you're rusty on that, don't worry. T is our time. Time could be years. It could be months. It could be days. It could be weeks. It could be hours. It could be minutes. Time could be any of those increments that we want it to be. It doesn't necessarily have to be years. It can be any of those increments we want. So let's go ahead. We've got the general form there and what each of the pieces means. So let's go ahead and dig in and actually apply it. So we have the inaugural, or first year, if you will. Attendance of an annual music festival is 150,000 people. The attendance, which we're going to represent with y, increases by 8% per year. The fact that we are increasing equals growth. If we are increasing, we are growing. So Miss Golly, how would I know this is the one to apply? We're increasing by a percent. We're increasing or we're growing by 8%. In letter A, we just want to write a function that represents the situation that we have. So the y in the function is the final amount. I don't have a final amount, so I'm just going to put a y. The a is our starting amount. How much do we start with? What's our initial amount? 150,000. Yeah. We start with 150,000. 1 plus our rate is our rate of growth in decimal form. So remember, to change that to a decimal, guys, we just take our decimal point and slide it 2 places to the left. So 8% becomes 0.08, not just 0.8, 0.08. If it grew by 80% each year, holy cow, this festival would be crazy out of control. You'd have the whole world there pretty soon. So we've got T is our time. We don't know how many years yet. It says in T years. So we don't know how many years has passed yet. We're just writing a general equation to represent our situation. Okay. Now you might be like, Miss Golly, why is there a 1 there? What this represents inside, 1 as a percent is 100%. So we're going to take 100% each time and add on another 8%. So each year we take 100% of our attendance and we add on another 8%. That's why the 1 is there. I always give people, Miss Golly, what does that 1 mean? 100%. So I'm going to take 100% of this year's attendance and add another 8% on. And then the next year we do the same. We take 100% of the attendance and we add another 8% on. So now that we have a function that represents our situation, let's see how we could use it. So letter B says, how many people will attend the festival in the 5th year? If I'm the person in charge of planning this festival, each venue can only hold so many people. And when you book venues for something this big, they can book out years in advance. So this person who is ever in charge, they have to check to make sure, hey, 5 years from now, with this festival growing at 8% every year, 5 years from now, am I going to need a bigger venue? Because if we do, we have to start shopping around now. So they need to project what the attendance might be 5 years from now to see, hey, do I need to find a bigger venue for our festival if it's going to keep growing at this rate? So 5th year, years are our time. So for the 5th year, that means our time is going to be 5 for 5 years. So all we have to do is take our function that we wrote in A, take our function from A, and put 5 in place of our t for our time. Now, if you want to clean this up a little bit, guys, I'm going to take that piece in parentheses, that expression, and I'm going to go ahead and add that together and just make it a 1.08. It's less for me to have to worry about computation-wise. It just cleans it up a little bit. So again, all I did was add the 1 plus the 0.08. That's all I did. So let's go to our calculators and let's figure out roughly how many people are going to attend this festival in the 5th year. On your calculators, if you turn them on, and let's say you pop up to maybe a table or a graph, to get back to your home screen to just enter this in to do the calculation, press your second key and then the mode button right next to your second key, and it will take you back to your home screen. So again, second key, and then press the mode key right next to it. It says quit above it in blue. So second mode, if you ever get into a menu where like, oh shoot, this isn't where I want to be, press the second key in the button right next to it, the mode key. All right, so we're going to enter in 150. 1,000. 1.08 is in my parentheses. And then exponent. Guys, I don't have a choice on here. I can't put different variables. I'm stuck with x. So I know the equation we wrote on our paper said t. All we can do on the calculator is the x. But actually, we need to put a 5 there because we're predicting. I thought we were graphing. We will graph this in just a minute. I'm a step ahead of myself. Sorry, guys. So we have 150,000. We have our 1.08 representing our growth. And then we want it 5 years from now. So we put a 5 for our time. Go ahead and press enter. And let's just go ahead and let's round that off to the nearest person. Okay, we can't have decimal parts of people. So 5 years from now, they are projecting that at this festival, there will be, and I'm going to put a little squiggly equals sign here because we're rounding. When you put the squiggly equals, it means approximately. It means approximately, so when somebody else reads your answer, they know you've rounded it. So we have approximately 220,399, and it's going to be people. Make sure we're doing application, so make sure that we are labeling. All right. So now the situation, we might go the other way. Instead of continually putting in different years for the time and seeing how we're growing, the person running the festival knows that, hey, once we hit, if and when we hit 400,000 people, we can't have our festival at this venue anymore. It just won't fit. So this person's trying to look ahead and say, hey, how many years do I have before we have to think about a different venue? So instead of putting in each year for the time, 1 year, 2 year, 3 year, and doing all that, let's go ahead and try to project for that total of 400,000. So I want my final amount to be 400,000. And then I want to know the piece that's missing then is my time. So you have to look at the information you're given. You're going to have the basic structure of the equation. You have to look at the information you're given and figure out what piece do I know and what piece don't I know. So in this case, I know my final amount 400,000, I need to figure out the time, how long it's going to take me to get there. Now, this isn't as simple as putting that in our calculators. We're not going to learn algebraically how to solve these this year. When you guys get to Algebra 2, you guys learn how to algebraically solve these. So we're going to go and rely on our technology. So we're going to go to our calculators. We're going to go to our y equals. Clear out anything that's there. We're going to clear out anything that's in that y equals, and we're going to go ahead and enter in our function of y equals 150,000 times 1.08. And then this is what I was talking about earlier when I got ahead of myself. When you go to enter this equation in to graph it, there's not going to be a t you can put there. The calculator is limited. I can only use x. So in our setup for our function, we had a t for time, and that makes sense to have t for time. When we go to use the technology, though, all I have is x. That's how this calculator works, and I can't change that. So you're going to have an x. Now, instead of trying to graph this, we're going to use what we've been using to help us graph. Go to our table, second graph. And what this table does, if you go ahead and scroll, here's where x is 5. Remember, x is our t, it's time. After 5 years, 20,399 people. After 5 years. So remember, this table, this is what we use to help us graph. When we just have some equations just to graph, this helped us get ordered pairs to graph. So all the ordered pairs you see on this table are part of your graph. They are solutions to your equation. They're solutions to your equation. There are points on your graph, which in turn are solutions to our equation. So as we scroll, we're looking for the attendance, which is my y. Y is my attendance. X is my time. I'm looking for my attendance to be over 400,000. And I'm going to hit that in what year? Year 13. So again, we can't algebraically solve these, but we can use our technology instead of trying to guess and check our way through. If you choose to not use the calculator, guys, what you would have to do is you would have to do like we did in Part B and just keep putting in different years. You'd have to put a 6 in for the t, and then the 7, and then an 8, and then a 9, until you finally had a total over 400,000. And that doesn't happen until year 13. So the calculator is putting in all of those different values for the time for us. We put the equation in, the calculator is going to do all of that work to put in 1 for the t, and 2 for the t, and 3 for the t, and 4 for the t. It's just going to quicken it up for us. We still have to have the understanding, though, of what we're looking for. The calculator is just doing the busy work. We still have to be able to interpret what it gives us. Okay? So, on the flip side of that, are exponential decay functions. If you notice, the basic structure is still the same. What's the only difference, though, between the growth setup and the decay setup? What's the only difference? It's a minus instead of a plus, yeah. There's the only difference. It's a minus instead of a plus. Because instead of adding on a certain percent each year, we're going to be taking it away. So if you don't like decay, decay simply means we're decreasing. If something's decaying, it's decreasing, or it's losing. However you want to phrase that. So growth means we're growing, we're increasing, we're getting bigger. Decay means we're decreasing, we're getting smaller. However else you want to phrase that. So if you're like, well, okay, Miss Golly, when would something like this come up? Well, for example, In 2016, I bought a minivan for about $42,000. It loses 10% of its value every year. So I want to be able to figure out, hey, after how many years should I think about getting rid of this thing so I get a decent trade-in value? How long should I make this minivan last? At what point is it no longer worth sticking parts into it to get it to run versus maybe I should trade it in and get as much money as I can out of it? So let's go ahead and write our function that represents the situation. Our t again is years after 2016 because 2016 is the year that I bought it. Doesn't seem like that long ago, but paying it off next month. It's already been 5 years. All right, so my y equals, my initial amount is 42,000. 1 minus 10%, and then I have my time. Again, I realize the 2 examples that I've done so far today, the time has been in years. It doesn't have to be, guys. It can be hours, minutes, days, months, weeks, seconds. Time can be any time increment. That's okay. Now, again, you might be like, Miss Golly, where does that 1 come from? Remember, the 1 is 100%. So it's 100% of my van's value. And then we're taking away 10% of that value. So the 1 is always there. The 1 is decimal form of 100%. The same way the 0.10 is the decimal form of 10%. So I'm going to take 100% of the van's value, and I'm going to take away 10%. So we've got our equation. If you want to simplify, guys, I would make this 0.90 before I try to do computation with it or put it in my calculator even. Make it as simple as you can. The less we have to work with to do calculations and enter into our calculator, the better off we are. All right, so the question is, I'm paying it off this year. So how much is my van currently worth? How much is my van currently worth? All right, so here's where this question, though, is a little bit different. My time. Last time when I was asked for 5 years, I just stuck a 5 in for the t. Am I going to put 2021 in for my t? Oh, 2021 years from now, guys, I sure as heck am not going to be here. And my minivan will probably have disintegrated long before then. So what do I put for the time? 5 years. 5 years have gone by. So it's not always as simple as, oh, I just take whatever time is there and throw it in for t. Sometimes we have to do a little bit of extra thinking. So from 2016 to 2021, 5 years have passed. 5 years have passed. So be very careful. I can't put 2021 in there. None of us will be around 2021 years from now. Holy cow. You never know. I mean, they could do a lot with cryogenics between now and then, but all right. So I want to get back to my home screen. Second, quit. Second, quit. Now I have 42,000 I start with. I've got that 90% in my parentheses. And my exponent, once again, is 5. That's just sheer coincidence. It's not going to be a 5 every time. Please don't memorize that or anything. It's not going to be a 5 every time. Go ahead and press enter. So my minivan that I paid $42,000 for 5 years ago is now only worth $24,800.58. Isn't that crazy how fast things lose their value? All right, so $sign for my label, $sign for my label, $24,800.58. And actually, guys, we don't need the approximate. We get to put an equal sign because we didn't round that. That's exactly what it came out to be. You just got to put the squiggly equals if you round. If you don't put the squiggly equals, people are going to think it's an exact value. Equal means exact, that it is what it is. All right, so if my minivan's currently worth $24,800.58, I'm paying it off next month. I'm starting to think about, oh, well, when the first major thing goes wrong with it, when do I get rid of it? So for me, when I started thinking about it, I'm like, you know, if that van gets to be under $15,000, it might be time to start thinking about trading it in. Because if I'm going to get another minivan, and if it's going to cost me over $40,000 again, I'd like to have a fair amount to trade in on it. So let's go ahead and figure out how many years it's going to take for that van to get under $15,000. So again, $15,000 is my end goal. So that's going to become my Y value. I still started with $42,000, still decreasing at 10%. But now in this case, I don't know the time. I don't know how long it's going to take me to get there. One course of action you can do is to literally guess and check. So do the process we did in part B. Put a 6 in for the T. Put a 7 in for the T. Put an 8 in for the T. Put a 9 in for the T until you get below the 15,000. You can do that. Or we can go to the calculator so it can do it for us faster. Let's go to our calculator. Let's go to y equals. Clear out what's there. 42,000. We have 90%. And again, I can't use t, I have to use x. Now, you might be thinking, before we jump to the table, you might be thinking, okay, Miss Golly, but what does this have to do with, we did all the graphing and things. Does this look like what we graphed? And it does. If we wanted to dig deeper into the graphing stuff, I just want to show you. I'm going to mess around with my window a little bit. And I'm just going to show you what this graph looks like. So it does look like our curves that we were working on graphing the last couple classes. We have an x for our exponent, or in this case it's a t, sorry. We have a variable for our exponent, so we do get that curvy shape. For us though, we're not quite at the place yet where we're ready to really use that graph. But technically, we are though. Because we're using, when we go to our table, we go second graph. When we go to our table, guys, that table is all the ordered pairs that make up that curve I just showed you. These are all the ordered pairs. You guys went to your table the last few classes to graph our exponential equations. This table is just a table of ordered pairs. We could plot those, but they don't look overly nice to plot though. They're getting kind of big on us. So let's figure out when are we going to get below 15,000. So I'm going to go to my y's, if it'll let me. All right, I'm going to go to my y's. I want to get under 15,000. So it looks like I could have my minivan for 10 years, and I should still be able to get, it'll be a little under, but probably around 15,000 for my trade-in, as long as we keep it in good shape. So it's going to take me 10 years. 10 years, approximately. So again, the thing I want to stress on this is that the time, because I don't want to stand up here and do every kind of example possible. You won't get any time to practice. Time doesn't have to be years. The two examples I chose, in both cases, time happened to be years, but it can be any time increment. Let's do one more example. Flip it over. In this particular example, this is an example of exponential growth because we have our plus, but it's compound interest. Now, maybe you've heard of it before. Maybe not, and that's okay if you haven't. Compounded interest is interest that you can earn on an investment. So for some of you out there, if you have a savings account, the interest on it might be compound interest. So compound interest means you get to earn interest not only on your principal, which is what you invest, but you also get to earn it on your interest as well. If you have simple interest, you only get to earn interest on whatever you invest. Compounded interest lets you earn interest on what you invest and any interest you earn. So you might be thinking, well, if I do have this in a savings account, you can figure out how long it's going to take you to get to a certain amount. And that can be a cool thing to do, especially if you have a goal in mind, something you're saving up for. So let's look at the different pieces of our equation. We have our P, which is our principal, and that's just our initial. And again, if you don't like that word initial, you can say starting amount. Our 1 is still there. Our 1 for our 100% is still there. Our R is our annual interest rate, and again, in decimal form. T is still our time, but now this one specifically, the time is in years. In this one, the time cannot be whatever we want. The time has to be in years. The only new variable we have on this one, we have an N, and that's the number of times interest is compounded per year. Now, you might come across a few phrases with this that you might not be familiar with. So if you hear semi-annually, semi-annually is going to be 2 times a year. Oh, I forgot an N in there. All right, so semi-annual, the interest is going to be compounded 2 times a year. Quarterly is going to be 4 times a year. And this one, I always like to say it. I'm hoping we'd figure monthly is 12, but again, for a lot of you, this is probably a new idea, so I want to make sure I get some of the basic phrases out there for you. So again, the N is how many times your interest is compounded each year. Or in other words, how many times a year do you get to earn interest on your interest? It's kind of cool. All right, so let's put this one into practice. Let's say you deposit $300 into a savings account. It earns 3% annual interest compounded monthly. Here's a keyword to let me know this is the setup I'm going to use. My interest is compounded. This is a compound interest formula. So if you're told interest is compounded, this is the route we're going to go. So let's go ahead and write a function that represents our balance. So we've got y equals, our principal is what we start with. 1 plus my rate is my R is 3%. It says monthly. Monthly means my N is 12. There's another N in the exponent, and then we don't know time. There's another N in the exponent, and then we don't know time. So the reason, again, I put the 12 is because we're compounded monthly. There's 12 months in a year. So my N is 12. Now, let's say you put that in there this year. You're like, oh, well, if I put that in there this year, and if you don't add anything to it, how much would you have when you graduate? So let's see. So how much will you have after 4 years? So the only thing that's going to change is the T is going to become a 4. The T is going to become a 4. Now, you might be thinking, okay, Miss Golly, so can I simplify that stuff in parentheses like we were doing with the other ones? Typically, guys, if we try to do that, we're going to end up with a messy decimal that we're going to have to end up rounding. And we don't want to round until the very end. So just leave what's in the parentheses alone. The part you can simplify to make your life easier is go ahead and make that exponent a 48. Go ahead and do the multiplication before we try to put this in our calculator. That's the piece we can simplify. We can control that. We can control that piece. We can control that piece. So to the calculator we go. I need to get back to my home screen off of my table, so I'm going to go second, and then the quit key right next to it. So second mode will get me back to my home screen. $300 initial deposit. 1 plus. Now to put the fraction in, if you have one of the newer 84 calculators, remember you can do alpha y equals, and you can get a fraction set up. But most of you have the 83s. So to do the fraction, remember we're going to use parentheses, 0.03, division key, 12. Close your parenthesis around the fraction. Close your parenthesis around the 1 plus the fraction. And then my exponent, we already simplified that. 12 times 4 is 48. Then you don't have to mess around with trying to make sure the 4 times 12 is part of your exponent. Simplify that time piece. All right, let's press enter. All right, so after 4 years, if you put $300 in this savings account, and this is if you didn't add anything into it, this would just be the $300, no other deposits or things that would change our total. So if you just put the $300 in and left it sit for 4 years, you would have roughly $338.20. So you would have made $38.20 doing absolutely nothing. Kind of cool how savings accounts work, right? Didn't have to do anything. You would have earned $38.20.
After 4 years?
After 4 years.
That is, no. You mean, bucks doing nothing.
Yep, so if you invest money in a savings account,
what if you invest money in stocks?
You earn interest. You earn interest. You do nothing. You just simply have your money in there, and the bank pays you interest for having your money in there.
That's squiggly line?
It's squiggly lines, yep. Squiggly lines, because we're going to round to the 20 cents. How many years will it take us to reach $400? Maybe that's your goal. How long do I need to leave that money sit? My goal is 400. My goal is 400. My ending amount is 400. And then I don't know the time piece. I don't know how long it's going to take me to get there. So you might be thinking, sweet, so if I just leave it sit for 4 years, if I don't need that money, I just leave it sit, I made over 38 bucks. How long do I have to leave it sit so I make 100 bucks for doing nothing other than opening the account? All right, so let's go to the calculator. Go to our y equals, clear it out. $300 to start. 1 plus. I need parentheses around my fraction. Close the parenthesis around my fraction. Close the parenthesis around the 1 plus my fraction. Then for the exponent, we have the 12. And instead of t, remember with this calculator, we have to use the x that we've been using to graph. We have to use the x piece. Now, you don't have to put a times in between there. Do not do that. Just put the 12 right next to the x, just like we see it on our sheet. All right, if we go to the table, second graph. Again, the calculator is just doing the busy work for us. The x column represents all of our t's, our time, our years. X represents how many years have gone by. Y represents the amount in my account after that many years. So after 4 years, we had $338.20. After 5 years, we see the amount. After 6, 7, 8. How many years does it take me to make over $400? Or not to make over, but to have over 400 in my savings? It takes me 10 years. It takes me 10 years. It takes me 10 years to get over that amount. Okay? It takes me 10 years to get over that amount. All right. So I know there's a little bit left on your sheet. We're going to pick up there tomorrow because I want to give you some time today to work on assignment 3 and ask questions.